So this tutorial is on wind loads and how to put them on buildings. So mostly working from AS 1170.2, which is structural design actions, wind actions. Now there's lots of asides here. Jump in with questions anytime and we'll let you direct this how it goes. First thing to say is there are two wind codes in Australia. This is 1170. There's also 4055, which is called wind loads on houses. And 4055 is basically a simplified version of this. And you can use it on houses and structures which are roughly the same size and function as a house. So it's designed basically for people who are designing houses. This looks pretty overwhelming when you first hit it, and so it's designed to be less overwhelming and a bit more friendly. So you guys who are doing that structure, start there and it's much easier to get your way through it. All right. So the first bit of the wind code. Now I'm mostly not going to go through the wind code. I'm mostly going to talk about how this gets onto structures, but we'll start here. The wind code starts with limitations for what you're doing, which is height of structure or that. And then the first section is all about how fast is the wind blowing where you are. So it takes into account the geography. There's a map of Australia there. You go here, yep, you've got the region. You've got what's on the ground, whether you're in an open airport field. Is that a question?
No.
Whether you're in an airfield, a forest, a dense building. Basically, if it's a dense city you're in, the wind gets friction. It doesn't blow as fast. Okay. So you put all those factors in. It talks about topography. If you're on top of a hill, you get extra wind speed. And what was the last one? Yeah, and then about the probability. So and shielding is there as well. We'll come to that after though.
Oh,
yeah, go on.
You know when it's got the sort of coordinates north, south, east, west,
yep.
and then it's got the factors for each one.
Yep.
And then some are bigger, some are less.
Yep.
I've never understood why that is.
Sure, I'll come to that in a second.
Okay.
What you have to do is select the return period. So there's a table here, 3.1. V1 is the speed that the wind is going to reach roughly every year. So in region A, 30 meters per second. Down to the wind speed that is going to come along roughly every 10,000 years, which is quite a lot higher, 51. Mostly, for most buildings, you're talking about a 500-year return period for your design wind loads. And these are ultimate loads. For serviceability, for deflection, you're talking about a lot less frequent. The direction multiplier you talked about, yeah, the wind blows in the region we're in, the wind blows hardest from the west, and from the north and the south and a few other directions, it's only 80 or 90% as much. All right. So what that means is for your particular site, you're going to end up with a wind speed in one direction of a certain amount. It's going to be a different speed in the other direction, different speed going this way and that way. So when you're designing a building, if you're going to take all the wind factors into account, you can have different values for wind blowing that way than you are for wind blowing that way. Okay? Then there's one equation, beginning of clause 2.4.1, which is how you turn the wind speed into a pressure. So there's a formula which allows for the wind speed squared, remember that squared, and the density of air. And basically, you put that in a formula, you get the pressure. And that's your basic wind pressure that you work with. And so you're going to have, obviously, with different speed, you've got different pressure going this way, different pressure going that way. Now, if you're designing a building, were you asking Todd why that's the case? It's just basically the wind, yeah, it's going to blow harder from the west.
Why?
Why?
I knew it was hard from the west. Why from the west?
I think that's getting into meteorological phenomenon. By the way, when you get into cyclone areas, you don't have the directional factors because when the cyclone comes, it like circulates, so it could be any direction.
Yep.
I don't.
The wind factors just always go to the west.
Yes and no. It's if you have a building, right? Let's say this is the building, and you don't know if they're going to build it that way around or that way around. Then yeah, you take the worst case because the wind could blow from any direction.
Yeah.
On the other hand, if you've got a massive roof and you know it's going to be the line this way, then if you're in the highest wind comes to the west, comes in this direction, you might have to make this side of the building stronger than you make that side, and that saves you money. For most small structures, you're going to pick the worst case wind and go with it. All right. So a lot of what we're doing today is actually going through how many load cases there could be, and there's dozens, and then selectively throwing some of them away, knowing which ones are less important than others. All right. So then, once you've got your basic wind pressure, then you go into chapter 5 of the wind code, and this is all about the shape factors. So we know the wind blows this way, it comes with a pressure. Now it's a matter of shape. So if the roof is a very steep roof, you get a different force on the roof than if the roof is very flat. So that's what we're all going into now. So the first one is, it goes through, is the internal pressure. And so this is about when the wind blows, there's an internal pressure inside the building. If you imagine a roof, a building, here's a plan, and it's got a big door there, the wind blows like that, the building tends to inflate. And it inflates, that lifts an upward pressure on the roof and the walls. On the other hand, when the wind blows this way, or from this direction, the building tends to deflate. And so you have to add that to the downward forces, the load cases there. All right. Okay, so tables 5.1a and 5.1b talk about the different internal wind pressures you're going to get. And so if I drew a diagram of a building here, and we'll consider basically a portal frame building. Is that coming out? Yep. In all cases. And so the internal pressure is either going to be positive, where it inflates the building, or it's going to be negative, where it sucks the building in. And the internal pressure always acts equally on all the surfaces, where there is a surface. So if that's like an open shed, the internal pressure acts there, but not on that, because there's no surface to act on. All right. So what you do then is you go, all right, let's get a building. Go a bit smaller. And let's consider the wind from this direction. Okay? If you look in, okay, the first thing gets you is an internal pressure. Depending on the openings, that's going to be inflation or deflation. Now, if you notice in this table for internal pressure, and for a lot of these tables, they give you two values. So, for example, leeward wall. Where's internal pressure gone? For example, if the windward wall is permeable, it gives you two values of -1 or 0.2. And that's a CFIG value that you multiply by that pressure you got from the wind speed. So -1 means you're going to have a deflation, or +2, was it -2 or +1, wasn't it? So -2 is the deflation, +1 is inflation. So you've got two possible internal pressures on the building. So we've already got two load cases. Okay. So we have to consider both of those possibilities when we're designing that. The next thing we're going to have then is we've got a load on the windward wall, which generally blows against the wall like that. That's pretty obvious. The wind blowing that way pushes on the wall. And on the leeward side, there's a suction off the back as well. Okay? And those are in tables. Windward wall is a very easy one. It's almost always 0.8. Leeward wall is another table. Windward wall is 5.2a. Leeward wall is 5.2b, and that value depends on a few things in the building, but that's relatively straightforward as well. We'll skip the side walls for the minute. I'll come back to that. And now we look at the roof. And the roof depends on the angle of the roof. So imagine, again, if you have a steep roof, the wind hitting it's going to have a different force on it than if it's a very flat roof. And so there's a couple of tables you've got to use in here. Generally, if it's less than 10 degrees, you consider it flat. If it's more than 10 to 15, 20, 25, you've got different values in that table you need to use. And also, even if you have a steep roof and you imagine the wind blowing this way, That you take as a flat roof because it's presenting flat surface to the wind. Did it stop? Let's keep it still going. Good. Okay. All right. So let's imagine we've got the roof like this. The wind is blowing that way. Let's call it a, well, it doesn't really matter how steep it is, but we get two different values. You get a value like that. So that's, when I draw that, that's a force lifting uplift on the roof. And I'm going to have a second value, which I'll draw here underneath, a slightly smaller value. That's on the windward side. And on the downwind side, it can either be the same if it's a flat roof, or if it's got a bit of a slope on it, it's going to be generally an uplift. On the downwind, sometimes you only get one value, which is nice. Okay. So, on the upwind side, say for a roof which is at 10 degrees, you might have, that might be 0.9 or 0.4. And you've got to say, why are there two different values? And the basic reason is that wind, when it blows, it flaps. And you imagine a roof, you always see it kind of going up and down like this. And the force will vary between those two values. And it could be either of them at any time. And the reason is, you can say, why don't you just give me the more severe one? The reason is, if you imagine you've got a suction, considering the case when you've got a suction force, and you've got this large force acting upwards, which counters it, you need to consider actually the smaller force, because that's going to be the more severe load case. Okay, I'll go through an example soon on this. All right. That's good. Now let's draw this in plan, this building. So let's say it's quite a long building, and you've got a wind blowing like this. If you look in the sidewall factors, you have a sidewall force which starts off quite high and then it steps down and then it steps down again. And same on the other side. And where it steps down is proportional to how high the building is. So, walls, where are we? Side walls are table 5.2c. And from 0 to 1h, you've got minus 0.65, which is quite a high force. Then 1h to 2h is 0.5, 2h to 3h is 0.3, and then 0.2. And so what's that saying is, up at the upstream side of the building, you've got a lot of force pulling these walls outwards, and that force just diminishes that as you go along the building. Okay? Again, we'll come to that soon. And then,
When the force is one like that, the roof, the two roofs,
yep.
You just treat that as a wall. You know, same force. So like,
Sorry?
so it's blowing that direction, and then the roof, so you treat that like 0.65 and then 0.5 the same.
No, this is just sidewalls. It's a different table on the roof. But since you're there,
Side elevation.
okay, let's draw this building on the side now. So again, we got. That'll look good.